Welcome to Introduction to Machine Learning for Data Science. In this lesson, part of our Data Science Fundamentals program, we'll explore how algorithms like linear regression, decision trees, and clustering help us discover patterns and predict outcomes. Machine learning is a cornerstone of modern data science, enabling everything from personalized recommendations to advanced analytics in healthcare. By the end of this lesson, you'll understand the basics of these models and where they fit in the data science workflow. Machine learning, ML, is the art of teaching computers to learn from data. Unlike traditional programming, where rules are manually coded, an ML model discerns patterns from historical information and applies them to new data. For example, analyzing thousands of past house sales can guide a system to predict future property prices. There are two main branches of ML to start with. Supervised learning uses labeled examples, like house features plus their selling prices, to train a model that predicts future outcomes. Unsupervised learning works without predefined labels, grouping or discovering hidden structures in data. Think about analyzing customer buying habits. You may not know which segments exist, but an unsupervised algorithm can cluster customers by similarity. Machine learning offers a range of models tailored to specific tasks. Linear regression predicts numerical values, such as pricing or sales, using a best fit line. Decision trees make hierarchical choices based on yes/no questions. Clustering groups data points to uncover hidden relationships. Each has its strengths and ideal use cases. Your choice depends on the problem you're solving, data available, and performance needs. Linear regression is a foundational supervised model that fits a straight line through data points, y equals mx plus b. For instance, if you track house size and selling price, linear regression can predict the price of a new house based on its square footage. It's easy to interpret. Each coefficient shows how much an input variable affects the outcome. Decision trees look like flowcharts that split data based on questions. At each node, the model asks something like, is the buyer's age over 30? Or, is the house bigger than 2,000 square feet? Ultimately, you reach a leaf node that predicts an outcome. Perhaps a classification, like likely to buy, or a numeric prediction. This structure is intuitive and easy to explain to stakeholders. Clustering falls under unsupervised learning, grouping similar data points together without labels. K-means is a popular method. It places centroids and assigns each data point to the nearest one, then iterates until clusters stabilize. Imagine segmenting customers by shopping behavior or identifying different species in wildlife tracking data. It uncovers hidden structures you may not know exist. Let's consider a mid-sized retailer overloaded with inventory data, seasonality, pricing, and store location info. By applying regression, they forecast which products will sell well. Decision trees predict which items are most likely to be returned. Meanwhile, clustering organizes customers by similar buying patterns, like frequent high spenders or casual bargain hunters. In healthcare, a hospital can use a supervised model, like logistic regression or a decision tree, to predict patient readmission risk based on age, medical history, and treatment plans. They might also apply an unsupervised clustering algorithm to spot new patterns among patient groups, highlighting potential correlations in symptoms or care outcomes. To master these concepts, practice on real data sets. Platforms like Kaggle and the UCI Machine Learning Repository offer free data, ranging from housing prices to customer churn. Load a data set, pick a target variable, and experiment with different models. For instance, try linear regression on a housing dataset or cluster customers in a retail dataset. Visualizations can make or break your ML insights. A regression line over a scatter plot shows how well the model fits. A partial decision tree diagram reveals how splits form predictions. For clustering, color-coded groups in 2D or 3D space give immediate clarity. Pair these visuals with numerical metrics, like accuracy or R-squared, to fully convey your model's performance. You don't have to start from scratch. Python's scikit-learn library offers ready-made functions for regression, decision trees, clustering, and more. For deeper neural networks, frameworks like TensorFlow or Keras come in handy. Platforms like DataCamp, Coursera, or Udemy provide structured lessons with interactive coding exercises. As you progress, You'll encounter advanced methods like ensemble models, random forest, gradient boosting, and hyperparameter tuning to refine your algorithm. You'll also face critical questions about model interpretability, ethics, and bias. Machine learning is increasingly integrated into financial, healthcare, and social systems, so ensuring fairness and transparency is vital. Let's recap the essentials. We covered linear regression for predicting numeric values, decision trees for branching decisions, and clustering for grouping data without labels. We explored supervised versus unsupervised learning, real-life examples in retail and healthcare, and resources for hands-on practice. By visualizing outcomes and validating model performance, you unlock powerful insights that drive informed decisions. Machine learning already drives personalized recommendations on e-commerce sites, fraud detection in banking, and predictive maintenance in manufacturing. Mastering these fundamentals positions you to harness its potential, reducing inefficiencies, boosting profits, or improving public services. This knowledge isn't just theoretical, it's transforming industries daily.